Hello, today we have this problem. It's technically two problems in the textbook, but I think they're way too related to separate them into different parts. Plus, I want to move on to the next chapter, next video. So yeah, let's begin. So we have a non-empty subset E, and we have this definition of distance of any point of the metric space to the subset, which is just an infimum of all distances. All points to the subset. We have to prove a few statements. First of all, that if it's gonna be equal to 0, then the point lies in the closure of E. So let's begin with that. Well, it's really easy to show it, but yeah, we also have to show this gonna be vice versa. If x belongs to the closure of E, then distance is gonna be equal to 0. Alright. So if we were to look into infimum, then what essentially it implies is that we have an infimum of 0. That means that for every alpha greater than that 0, there exists some element belonging to this set of distances. Exists some distance x, z belonging to the set of distances. So let's call this set I. And let's denote it over here. Actually, Ix. We're gonna denote it as the set of distance between x and z, or z being just an element of E. Alright. That is gonna be less than alpha. Alright, and this can be rewritten as for every radius greater than 0, axis is z belonging to E, such that the distance between x and z is less than r, and essentially this is the definition of a limit point. And what this implies is that, well, x is a limit point, and therefore it belongs to the closure. There's also an alternative, you could say. Well, if we were to take some greater than 0, okay, yeah, there's an alternative. Either it's a limit point or it belongs to E, because dx z can be less than r if it's like dx and x. So it doesn't conform to the definition of a limit point because p is equal to q, but the distance is still gonna be qualified by the fact that x belongs to E, so it does belong to the closure. It's either a limit point or belongs to E. Alright, and before we go to B, we have to prove the converse. So number 1 is x belongs to E directly, so it's not specifically a limit point that doesn't belong to E. And what does it mean? Well, if x belongs to E, then its infimum is going to be 0 for sure, because we can just take dxx, which is equal to 0. So I don't see any point to write more down. And if x does not belong to E, although x belongs to the closure of E, in other words, x is a limit point, then for every epsilon greater than 0, exists z belonging to E, such that the distance between z and x is less than epsilon. And now the thing is, we can sort of rewrite this for Again, whether we've been playing the infimum. Okay. So let's take alpha as 0. For every... Well, actually, for every alpha greater than 0, here we're working the similar way as here, exists dzx belonging to x. Again, we're just mapping z to dzx, sort of, hence why it exists, such that dzx is less than alpha. And again, this is just basically the definition for the greatest lower bound. So indeed, the infimum is going to be 0. Now if we were to look into the point B, we're asked to prove that it's uniformly continuous on X by showing this inequality, for X and Y. And we're given a hint that severely simplifies it, because if we were to take this inequality and this inequality, here we can just move row of y to the left hand side, get row e of x minus row e of y is less than or equal to dxy. Well, why don't we don't have the absolute value here? What we can do is we can apply this inequality for x2 being equal to y and y2 being equal to x. And what we're gonna get is the same exact inequality, except here we have d of yx, which is equal to dxy, so the same thing. Here we're gonna have the opposite, re of y minus re of x, so you can just put the absolute value here safely. Now we have to show that this implies that the function is continuous. Well, for every epsilon greater than 0, and have here actually implies that we can pick delta is just what? Well, this thing is going to be less than this thing. So if we make the xy less than delta less than epsilon, it's going to work. So we just need any delta less than epsilon. So let's pick delta as epsilon over 2. So for every x and y, I'm being stupid. For every y, such that the distance between x and y, actually we're working with a real function, I can use the absolute value here. X minus y is less than delta implies that row of oh wait, no, I'm stupid, actually. dxy is less than delta implies that this thing is less than delta, and then it's going to be less than epsilon, so or e of x minus or e of y is less than epsilon. Now, reason why I denote it here as d is because we're working with some arbitrary metric space, and the function maps it to real numbers, so I can use the absolute value after. So it's definitely a real valued continuous function uniformly. Alright, now the next part. Have disjoint sets in a metric space X, there we call K and F, and K is compact and F is closed. I have to show that there exists delta, so that basically the distance between these two sets is greater than this delta. If P belongs to K and Q belongs to F. Have as a hint that we can apply the previous problem here directly. Have to show that the conclusion may fail for two disjoint closed sets if neither is compact. So let's begin. First of all, the row of F is going to be continuous positive function k because, first of all, it's defined in a way that implies that it's positive. Second of all, if we were to look into this, why is... Okay, it's implied to be non-negative. Why is it positive? Well, if we were to look into row f, first of all, it's continuous on k by analogy, as here it's continuous on x. The logic is basically the same. You can apply it to this x, and then it's going to be continuous on this subset. Alright, now, if we were to look at row f, then row f of k is also going to be compact. And if it's compact, then, well, let's take the infimum and call it alpha. And let's say that alpha greater than 0. Well, then it's fairly simple. That implies that there exists delta greater than 0. Okay, what about if alpha is equal to 0? Well, then that implies that since we're working with a compact set, rule f of k is going to be compact, so every limit point belongs to this. And the issue here is the fact that the 0 is going to be included as a limit point, because infimum here is basically kind of like a limit, like it was here. Okay. So this implies that exists z belonging to k such that rho f of z is going to be equal to 0, but this implies that exists z2 belonging to f such that d z z2 is equal to 0, which implies that z is equal to z2, which can't be true because we're working with disjoint sets. Now, the reason this wouldn't work for two disjoint closed sets is the fact that it's not certain that if we were to fit a closed set into a continuous function, we're going to get a closed set back. And we need to provide an example, I guess. Well, let's take the real number line. We were to make some monotonically rising sequence, and that adds some monotonically decreasing sequence on top of it that converges to 0. So we get the second sequence, which is just the sum of two sequences. You can see that essentially it's slowly decreasing the distance. However, neither of these converge, so the limit points definitely are contained within. And as an example to this, let's take 2 to the power of k and 2 to the power of k plus 1 over 2 to the power of k. We're doing that for k greater than or equal to 1. Alright. So that's it for today, yeah? See you in the next video. Bye.